Welcome you all in the 25th lecture of Electronic Measurements and Instrumentation. In this lecture, I will discuss a transducer which converts change in temperature into change in resistance, that is the thermistor. So, in this lecture, I will discuss about the thermistor, that is the thermal sensitive resistance. So, I will cover my lecture by from introduction of thermistor, what is the function of a thermistor, how it functions, and what is the basic principle of thermistor, then type of thermistor, what are the different characteristic of thermistors, application of thermistor, and advantage and disadvantage of the thermistor. So, thermistor is basically it is an abbreviation of thermal sensitive resistor. So, that is why it is known as thermistor. Thermistor is a transducer that converts change in temperature into change in resistance. Since it requires an auxiliary source for conversion of change in resistance into change in voltage, so it is a passive type of transducer. So, thermistor is a passive type of transducer and it can be used for the temperature range of minus 60 degrees centigrade to 300 degrees centigrade, and its resistance changes from zero point 0.5 ohm to 0.75 mega ohm. It means the variation is very large. It is from 0.5 ohm to 750 kilo ohm, and the temperature variation that is measures from minus 60 degrees centigrade to 300 degrees centigrade, means for 360 degrees centigrade the variation is in temperature is approximately 750 kilo ohm. So, it has a very large range of resistance variation. It means its sensitivity is very high, and we can see here for every 1 degree rise in temperature there is a decrease or increase of 5% of their resistance. So, for every 1 degree change in temperature there is a change of 5% of its resistance. So, sensitivity of thermistor is very high. Now, thermistors are of two types. One is NTC thermistor and other is PTC thermistor. NTC stand for negative temperature coefficient of thermistor. Negative temperature coefficient means when temperature increases its resistance decreases. When we are using a semiconductor material, we know that when temperature increases its conductivity increases and its resistance decreases, because when temperature increases the number of free electron also increases. So, when number of free electrons increases means conductivity increases and resistivity decreases. The other is PTC, positive temperature coefficient of thermistor. This is in PTC thermistor, when temperature increases the resistance also increases. So, we know that in metal when temperature increases, since there are free electrons already available in metals, and when the temperature increases the number of free electrons also increases and their velocity increases, and because they will collide each other and the resistance of this metal is increases. So, PTC is generally made up of polycrystalline or made up of metal material, and NTC is made up of semiconductor materials. So, NTC is of two type, bead thermistor type and disc and chip type, and PTC is of cylindrical type thermistor and switch type thermistor. So, there are two type of thermistors we are using in daily life, one is NTC and other is PTC. So, how do we select a particular thermistor for a particular purpose? So, first of all the selection criteria is what is the temperature range, the high and low temperature ranges necessary for that particular application. Then what are the budget for that thermistor, whether we need more accuracy, so we or more precise measurement, then we go for the costly thermistors, otherwise we can purchase any type of thermistors. Then what type of accuracy needed. So, that is also when we select a particular type of thermistor, then accuracy is also an important factor. Accuracy means ki how close the measured value is with the true value. Then the atmospheric conditions. At what atmospheric conditions we are going to use that particular thermistor. So, whether it is used in the oxidized conditions or not. Then level of exposure that is expected means how quickly we need the response. Suppose if a system the temperature is varying very uh, temperature is varying very fast, then we need a thermistor that will respond that fast change in temperature. Then what lifetime required for that particular thermistor, and thermistor whether it is we are using the thermistor in continuous process or we are using in the irregular process, means we are using in intermittent or the continuous process. Then whether the thermistor is subjected to twisting or flexing all through the device lifetime. So, these are the parameters by which we are selecting the particular thermistors. Now, first I will discuss about the PTC thermistor, positive temperature coefficient of thermistor. So, PTC thermistors are the resistors with positive temperature coefficient. PTC thermistors are a transducer whose resistance changes with the change in temperature, and the change in resistance is positive, means when temperature increases the resistance also increases. So, based on the structure and manufacturing process, the PTC is of two types. One is Celestor type and other is switching type. So, in Celestor type it is made up of silicon and it have linear characteristic. So, we will see that this Celestor type is made up of silicon and it has a linear characteristic, whereas the switching type thermistor is made up of polycrystalline ceramic material, and this switching type thermistor has non-linear characteristic, and they are generally used for the self-regulating heaters and as a resettable fuses. So, we can see in figure these are the Celestor type thermistor and this two is the two are the switching type thermistors. So, these are the typical characteristic of a PTC thermistor. One is, we will discuss two type of characteristic. One is temperature versus resistance characteristic and other is current versus voltage characteristic. So, we see in this figure temperature versus resistance characteristic. We have studied two type of PTC thermistors. One is Celestor type and other is switch type. So, we can see from this figure that Celestor type has a linear change in resistance with change in temperature, that is there is a linear relation between change in temperature and change in resistance, but we can see that the change in resistance is very low, means the range of change in resistance is very low. The temperature changes, but the change in resistance is very low for the Celestor type. So, we can't use Celestor type for a very sensitive, where the sensitivity needed more. But in switching type we can see that after the this critical temperature, or we can say after the transition temperature, the resistance increases very sharply. So, we can use this type the switching type PTC for the where we need a very sensitive type of device. Here there are 2 points. This is R25, that means at 25 degree centigrade we generally define the value of the resistance in case of PTC. So, generally the thermistor which is PTC type, their resistance is defined at the temperature of 25 degree. So, it is R25. Then this is a Curie point, this TC is known as transition temperature or the Curie temperature. So, this transition temperature is defined as the temperature at which the change in here the change is negative, the change in resistance is negative in till this point, and after this point the change in resistance is positive, means when temperature changes the resistance also changes. This in general this Curie at the Curie point or at the transition point, the resistance of the thermistor in case of switching type thermistor, it is twice of the minimum resistance. So, we can see that till this point, till critical temperature or till the Curie point, the resistance of the switch type thermistors are decreasing, but after that point the temperature when temperature increases after Curie point, Curie temperature, the resistance increases sharply. So, these switches are used in many purposes. Then we can see the second diagram, that is the current voltage characteristic. So, we can see in current voltage characteristic till ambient temperature, when the current increases, the voltage drop across the temperature also increases. Now, it at that time when temperature current in when this voltage drops increases, the current sharply increases, but after that at after the ambient mode, ambient temperature, when the thermistor is in self heated mode, means when we increase the current, the thermistor get heated, and when thermistor get heated, its temperature increases. When temperature increases, then its resistance also increases. Since resistance also increases, the current decreases. So, this curve shows that before the ambient temperature, the current increases, but after the ambient temperature, since resistance increases, the thermistor will go in self heating mode. It is self heated, and when the thermistor is self heated, the resistance of the thermistor will increase, and that is why the current will decrease. Then what are the different application of PTC? So, PTC we use for the self regulating heater. We use the thermistor at our home in refrigeration. We are using the thermistors for the geyser. In the microwave we are using the self heating thermistors. So, we know that when the current is flowing through the thermistor, when thermistor get heated, then it regulates the temperature. So, if there is a current running through a switching PTC, it will auto stabilize at a certain temperature. Then second is overcurrent protection. So, in overcurrent protection, switching PTC, again we are using switching PTC for many purposes, because switching PTC has a very wide range of change in resistance. So, in overcurrent protection, the switched PTC thermistors are used for the overcurrent protection and for the resettable fuses. So, in this case, an overcurrent situation, the thermistor body temperature rises. Suppose we have placed PTC thermistor at a place, and when the current increases, its resistance increases, and when its resistance increases, then because of the increase in resistance, the current is controlled. So, it will protect the overcurrent protections. So, they are used for many purposes, and they are known as under different names, like such as polyfuse, polyswitches and multifuse. Then time delay. When we need a delay time, like in fluorescent lamp, we need that a small current is flowing through the fluorescent and it will ignite it. So, for this purpose we are using a PTC, and when PTC get heated, then the current will decrease. So, a time delay in a circuit can be provided by using the time needed for the PTC thermistor to heat up enough to switch from its position to the higher resistance state, and vice versa. The time delay depends upon the size of the thermistor, the ambient temperature and the voltage it is connected to, as well as the circuit in which it is utilized. Then motor starting. In many motors, we need a special type of winding. A special type of winding is provided, which is known as startup winding. So, when there are separate startup winding which need to be powered only during the starting period of the motor. So, at that time when we connect the PTC thermistor with that startup winding, so when the current is when the current flowing through the PTC and the startup winding, then the current will flow through the winding and the magnetic field will be induced there and the motor will start. But after certain period of time, after the ambient temperature, the PTC thermistor will get self heated and in self heated position its resistance increases, and because of increase of resistance the current will decrease, and after certain time when resistance is very high, no current will flow through that circuit. So, these are the applications. We can use PTC for self regulating heating, for overcurrent protection, to provide delay time, and to provide starting of the motor. So, it can also you start the motor when different starting coil is used, starting windings are used. So, these are the application of positive temperature coefficient of thermistor. Now, negative temperature coefficient of thermistors, these are of two type. Since it has a negative temperature coefficient, means when temperature increases, its resistance decreases, and it is made up of from cast chip of semiconductor material such as sintered metal oxide like magnesium, nickel, cobalt, iron, copper and titanium. So, they are basically classified into two category, bead type thermistor and metallized surface contact. So, depending upon the alloy used in that and the shape of the thermistors. So, bead type thermistors made up of platinum alloy, bead type made up of platinum alloy, and the lead wires are directly sintered into the ceramic body, and it offers very high because its leads are centered in the ceramic body. It offers very high stability, reliability, fast response time, and operates at very high temperature. And this bead type has it requires very less space, and it can be fitted at any place. So, bead type thermistors are used at many places. So, bead type thermistors are included following type: bare bead, there are different type, that is bare bead, glass coated bead, glass rugged bead, minimized glass bead, that all depends upon glass probe, glass rod, bead in glass enclosed. So, we can see here that it is this type, bead type, rod type. So, there are many type of thermistors that are come under the bead type thermistors. And then there is other type, that is the metallized surface contact. Bead type thermistor generally used in is enclosed in glass, because it will not be impacted by the change in weather conditions, and it should be rugged. But metallized surface contact type available with the radial and axial leads as well as without lead. Metal surface contact type is available in the IC form, and it is also available in the surface mounted form, means surface mounted devices which are placed on the PCB board. So, it is available at the disk type, chip type, that is IC type, chip type, surface mounted type, flak type, rod type, and it is also available in the form of washer type. So, that we can put here at any place. The relationship between the resistance and temperature of the NTC thermistor. So, this RT is equal to R naught e to the power beta 1 by T minus 1 by T naught. This is the relationship between the rise in temperature. So, here R naught is considered, means R naught is the temperature at T naught. We can also calculate the value of RT from a particular temperature to the second particular temperature. But here I have considered the R naught as a resistance as temperature T naught, it is in Kelvin, and RT is the resistance as temperature T. T naught is the reference temperature. Here reference temperature is taken, and it is normally considered as 25 degree centigrade. Beta is a constant, and its value depends on the characteristic of the material which we are using for the manufacturing of NTC thermistors. And normally the value of beta varies from 3500 to 4500, and nominal value we can take as a 4000. From the above equation we can see that this RT is varying exponentially when temperature increases. So, this is the advantage of NTC thermistor, that there is a large variation in resistance when the temperature increases. But what is the drawback of this? That linear approximation of the curve over even a small temperature range is not possible, and hence the thermistor is very definitely a non-linear sensors. So, when we want to measure the change in resistance by measuring change in temperature, we want to measure the change in resistance, and then thermistors are a passive device, then we have to use a auxiliary voltage source there. So, when change in resistance is converted into change in voltage, so that change in voltage is also non-linear. So, we need a setup, we need a meter which can measure the non-linear change in voltage. So, scale should be non-linear. So, if the value of beta is very high, the resistor temperature relationship will be very good. We need a material whose beta should be very high. A higher value of beta means the higher variation in resistance for the same rise in temperature. Hence, the sensitivity is more. So, next we can define the temperature coefficient. So, temperature coefficient alpha T is equal to 1 by RT dRT by dt, and it is equivalent to minus beta by T square. So, temperature coefficient, here negative sign is shown, means this is for the negative temperature coefficient of the NTC thermistor. It means the resistance temperature characteristic is negative. Now, if beta is equal to 4000 Kelvin and T is equal to 298 Kelvin, then if we calculate the value of alpha T, then it will become minus 0.0045 per degree Kelvin. This is much higher than the RTD. If we are using a platinum RTD, it is very costlier, but the sensitivity of thermistor is negative NTC thermistor is very much higher than the platinum RTD. So, this would be able to measure a very small change in temperature. Now, the characteristic of negative temperature coefficient thermistor. So, there are three important characteristics that I will discuss. One is the resistance temperature characteristic, second is voltage current characteristic, and third is current time characteristic. So, first I will discuss about the resistance temperature characteristic. So, as we know, it's NTC thermistor, that is negative temperature coefficient of thermistor. So, its when temperature increases, its resistance decreases and it is exponentially decaying. Then second curve is the voltage current characteristic curve. So, voltage current characteristic curve, we can see when the current is very small, the voltage when current is very small, the voltage rises because the resistance is less. But when after a certain period of time, when current increases, it will go in self heating mode, and then the resistance decreases and the voltage drop across that is also decreasing. Then second is time delay. So, we see in current time characteristic that when the current is increasing, the time is also increasing, and this time delay depends upon the input voltage which we are applying from the auxiliary source. So, if input voltage is, we see here that if input voltage is 80 volt, then the delay is less, but if input voltage is 60 volt, the delay is more. So, that means the delay in process or the time delay depends upon the voltage applied and the current flows. So, we can design delay circuit by using this property of the negative temperature coefficient of thermistor. So, application of NTC. So, first of all, we can measure the temperature, and for measuring the temperature, since the thermistor has negative temperature coefficient, so its resistance decreases when temperature increases, and we apply a battery E here because it is a passive transducer. So, we need a battery. So, when the current is flowing over here, when the current increases, and it will get in self heated mode, then the temperature increases, and when temperature increases, then resistance decreases, and so the current will increase. So, we can use PMMC instrument for the measurement of the current which is flowing through the thermistor, and if we calibrate this in terms of temperature, then it will show the temperature. Similarly, it is used for the temperature compensation because its resistance decreases when the temperature increases, and there are many devices whose resistance increases when temperature increases. So, we can use this thermistor in parallel to that, and this will share the current flowing through that, and it will compensate the change in resistance at that particular place. Then third is the control of temperature. This thermistor is connected in the bridge form, and there are 10 kilo ohm, 10 kilo ohm, 4 kilo ohm resistance. So, when the bridge is in balance condition, there is no current through the amplifier, and the relay is in off mode. But when there is a current, when there is a temperature here over here, then the bridge is in unbalanced state, and when it is unbalanced state, then the current will flow through it and it will compensate it. Then it is used for the surge protection, that means if high current is flowing through it, then we can use for this thermistor, because after some certain period of time the resistance of this negative temperature this NTC thermistor will reduce. Then similarly, temperature control alarm, we can use it when this has high value of resistance, the small current is flowing, but at self heating mode its resistance will decrease and the current will increase. So, if temperature decrease at any microwave oven or any place, then it will get we will get an alarm that temperature is decreasing, because the resistance is high and so low current will flow through it. And when the alarm, it will give an alarm, then the temperature can be increased. So, these are the thermistor applications. So, first this is the wall mounted thermistor that we are using at our home in a refrigerator, and in different places in AC we are using it. Then this type of used for the circuit protection. Then in digital thermometer also thermistors are used. In digital thermometer, the traditional thermometers, the mercury is used, but in digital thermometer thermistors are used because it is very sensitive. Similarly, these thermistors are used in the temperature measurement of ducts, tanks at other places when remote sensing is required. Similarly, commercial application we are using it in the vehicles like car and other places where the cabin heat measurement is required and controlling is also required. Similarly, in 3D printer, since the ink is in molten form, so for measuring the temperature of that particular ink is also we can use thermistor. Similarly, food and beverage industry also uses thermistor, because in food industry also we want to monitor the temperature at very places and in environment also. So, these type of components are used over there. In medical, in incubator centers where when the newly born babies are kept, so thermistors are used because it is very sensitive and very fast changing response. Similarly, it is also used in fluid and gas flow places. So, this is one property of the thermistor, that when it is self heated and if the water or any thing is flowing over there, then there is a change in temperature, and that change in temperature is described by the change in flow. So, these are the uses of temperature. We are using it in digital thermometer, household applications like microwave, fridge, oven, and for the circuit protection. In rechargeable battery also we are using it, because it ensures that after a particular temperature reaches, it will break the circuit, otherwise our battery will get distorted. So, thank you all from my side.